This is Cisco Training 3, Classful IP Addressing. I'm Darrell Root. If you have feedback, you can email me at ciscotraining@mac.com. And I also have these podcasts are available via iTunes Podcast, but I also have them available on my personal webpage, http://web.mac.com/DarrellRoot. Before we get into today's session, I want to recommend a book, CCNP Practical Studies. This is a great book where they teach intermediate routing and IP addressing, and they use practical examples. And so it's, well, I just like the book. I think it's useful. Let's go into today's session. Today we're talking about classful IP addressing. And one of the things I wanted to show you was the format of an IP packet. This is the format of an IP version 4 packet. At the beginning we have the version number, which for most of the internet today is version 4. We're migrating to IP version 6, but today almost everything that you go to on the internet is IP version 4. Bunch of other stuff in the packet header, which I'm not going to go into today. That'll be a later session. But there's 32 bits for the source address, and there's 32 bits for the destination address. Anytime you're sending data on the internet, you're sending an IP packet. That IP packet has a header. A source address and a destination address are in that header. You're used to, on the web, going to places like www.google.com or www.cnn.com. When you do that, you don't, from the network perspective, the network resolves your host name into an IP address, and then the network forwards to the IP address. So, for example, there's a command in Unix, and Mac OS 10 is Unix. There's a command called host. So I type in host, darrellroot.com, and it says darrellroot.com has address 216.21.229.209. If you type in darrellroot.com in your browser, it looks like you're going on the internet to darrellroot.com. But what the browser really does is the browser looks up, using something called the domain name service, the browser looks up this and identifies that darrellroot.com is really this IP address. And then the browser is sending packets to this IP address, and this IP address is responding. That's how the internet works. Now, an IP address is 32 bits. So let's see what an IP address looks like. This is an IP address. It is 32 bits in length. You know, that's sort of hard to remember. 000010100010. It's insane. So what do? To make it easier to remember, the first thing that we do is we break the IP address into octets. There are 4 octets in an IP address. Each octet is 8 bits. That's why they call it an octet. So this is a little bit easier to read, but it's still not that easy to read. Then what we do is we convert each octet into decimal. So this octet here, this is the 1's bit, this is the 2's bit, the 4's bit, the 8's bit, and so on. So it's 0 plus 2. So 1 times 0 plus 2 times 1 plus 4 times 0 plus 8 times 1 plus 16 times 0 plus 32 times 0 plus 64 times 0 plus 128 times 0. So this is 8 plus 2, which is 10. Here, 1 plus 2, not plus 4, not plus 8, not plus 16, plus 32. So 32, 33, 34, 35. 10.35.1 plus 2 plus 4, that's 7. And here, 0 plus 2 plus 4 plus 8 is 14. So that big long IP address that we saw, this big long IP address is actually 10.35.7.14. So when you're looking at it in the network, you might look at it as darrellroot.com, or you might look at it as 10.35.7.14, but never forget, it's really just 32 bits that are either ones or zeros. A classful IP address has two parts. It has a network part and a host part. So here's our 32 bits, and let's go ahead and break 2, 4, 6. Let's go ahead and break it up into. Let's go ahead and break it up. There we are. So here's our IP address again, broken up a little bit. This is a classful IP address. It has a network part and a host part. Now the question is, how do we know what's the network part and how do we know what the host part is, and what does that mean anyway? So there are three classes, the classful IP addresses for unicast, which is all we're going to talk about today. There are three types. A class A is where the first bit is 0. So this IP address is a class A IP address because this bit right here is a 0. What that means is a class A has every IP address starting from 0.0.0.0 to 127.255.255.255, because all of those IP addresses in that range start with 0 right here. So 10.35.7.14 is a class A because the first bit is 0. A class B IP address is where the first two bits are 1, 0. So let's go with the rules. Class B, the first two bits are 1, 0. So a class B includes every IP address from 128.0.0.0 to 191.285.285.285. Likewise, a class C IP address is all the first three bits are 110. So a class C is all IP addresses from 192.0.0.0 up to 223.285.285.285. Now, there actually are Class D and Class E IP addresses. We're not going to talk about those today. Those are the IP addresses starting with 224. So what that means is when a router sees an IP address, the router can identify, just looking at the first three bits, it'll know whether it's a Class A, a Class B, or a Class C. And it can handle the packet accordingly. Now, what exactly does a Class A mean? A Class A means that the first 8 bits are the network portion, and the remaining 24 bits are the host portion. So in this 10.35.7.14 IP address, the router knows that's a Class A. The first 8 bits, or the 10, is the network portion. The rest is the host portion. So we have 24 bits for host portion, which means that 24 bits is roughly, what is that, 4 million, let's see, it's 10, 20, 1,000 million, 2, 4, 8, 6, it's like roughly 16 million possible IP addresses inside that Class A. So you have a network, you know, 16 million hosts in your network. Cool, that's great. For Class B, the first 16 bits are the network portion, and the last 16 bits are the host portion. So there's a lot of, so the Class A networks, there are only 127 possible Class A networks, or 128 possible Class A networks. Class B networks, you can have, there's, you know, tens of thousands of Class B networks, and each one can have 65,535 hosts or so. Class C network, the first 24 bits are the network portion, and the last 8 bits are the host portion. So there's millions of Class C networks, but there are only 256 possible IP addresses in each. So that's So we have 2 to the 24th power hosts, roughly 4 million for Class A, 2 to the 16th power hosts, or 65,532 for Class B, 2 to the 8th host, or 256 for Class C. Or rather, that's not really hosts, it's IP addresses. We'll talk about that. Okay. Here's the problem. The reason this was done is back in the early development of the internet, there were large sites, there were medium sites, and there were small sites. So they divide the network and they design the network. So you have Class A's, so you have a site that's going to be pretty large, like Digital Equipment Corporation or MIT, and so they get a Class A. And then you have sites with a a medium number of hosts. Most universities got Class B's. And then you have a small business, you got some network at home. That's great for a Class C. But who needs a subnet, one Ethernet domain, one Ethernet LAN with 4 million hosts on it? Nobody. You can't put 4 million hosts on an Ethernet network. It'll melt. So you've given MIT this Class A where they have, or you've given this corporation or large university a Class A where they can put millions of hosts on it, but they really want to have multiple subnets. So what we do is we do subnetting. So what subnetting is it's a sort of an interim solution to improve the efficiency of the network, to allow you to have more networks and route between them. So what you do is you take your Class A network, which is supposed to be a /8, meaning that it has 8 bits for the network portion, and instead, after the network portion, you put in a subnet portion. So let's say we take these other 16 bits, and we call that subnet bits. So what that means is that the first 24 bits will be a network, and the last 8 bits will be the host on the network. And that is called a /24. Then you have something called a subnet mask. The original subnet mask for the classful /8 is 1s for the network portion and 0s for the host portion. And that way you can, given any IP address, you can figure out what the network identifier is by doing a bitwise AND between the IP address and the mask. It's like an AND mask. So if we did a bitwise AND between this IP address at the top, which is really 10.35.7.14, and 8 ones and then all zeros, what we'd end up with is this 000011010, and then it would be all dot zeros, because anything and 0 is 0. That's why it's called a mask. So this is the network. So the network portion for 10.35.7.14/8, which is the natural classful network mask, is 10.0.0.0. That's the network for it. /8. But we want to do subnetting. So instead, we're borrowing some of the host bits and turning them into a sort of additional network bits. So our mask is actually now a /24. And so our new subnet mask is one, and so on for 24, and then zeros. And so when we do the bitwise, what that means is when we do the bitwise AND, this bit becomes a 1, these 2 bits become 1s, these 3 bits become 1s, and our network is 10.35.7.0/24, and then the host portion is the .14. Okay, great. One other subnet mask of interest. Well, there's lots of other subnet masks of interest. In fact, there's exactly 32 network masks in total. Some more useful than others. One of the network masks is this one. The first 30 bits are ones, the last 2 bits are zeros. This is a /30. So if we do the bitwise AND between our IP address here and this /30, what we get is we get the first 30 bits and then a 00. And that's our network identifier. So here's our IP address on the /30. Here is our network mask. We do a bitwise AND, and then this is our network. So our network for 10.35.7.14//30 is 10.35.7.12/30. Now that /30, we can change the last 2 bits to be our host portion. And so our host portion can be 00, which is the .12, or it can be 01, which is the .13, or it can be 10, which is the .14, or it can be 11, which is the .15. So let's write all of those out. So our valid IP addresses in this subnet are .12, .13, .14, and .15. But you know, we can't use all of those IP addresses because some of them have special meaning. The IP address with all zeros in the host portion, which in a /30 is the last 2 bits, is reserved to identify that network in the first place. So since this identifies the network, we can't use this for a host on that subnet. And the IP address with all ones at the end, like this one here, which corresponds to the .15, is called the IP directed broadcast address. If you send a packet to a IP address which it has all ones in the host portion, then the behavior of the routers is to send that packet to all hosts on that subnet. Or at least that was the behavior years ago before hackers started doing this, and then router vendors turned it off by default. So this is so on this /30, which has 4 valid IP addresses, only 2 of them can be used for hosts, .13 and .14. That's what makes the /30 interesting, because if you're connecting a router to another router, you need exactly 2 hosts. And so network engineers that use their address space efficiently use a /30 for that, which is great. Okay, what other combinations can't you... Well, let's talk about a /24 for a bit. So let's say we have a /24. So our IP address is now a /24. And so our network mask is now all ones for the first 24 bits and then all zeros. And so we do the bitwise and our network identifier is... So we do our bitwise AND between our IP address and our network mask, and so we get the network identifier. So the network identifier is now 10.35.7.0/24. In this network, there are 8 bits here, so there are 256 possible IP addresses. But again, we can't use the IP address, which is all zeros, for an actual host. And we also can't use the IP address, which is all ones for the last 8 bits, for an actual host, because that is the IP directed broadcast. address, which means that even though there are 256 possibilities, there are only 254 valid hosts there are 254 valid hosts out of 256 possibilities when on a /24. So a /24 is a pretty good breakdown for a typical usage subnet. You can put a couple hundred hosts on it, which is substantial, but if you've got a in this case we have a class A, so we have 24 bits for our subnetting. So if we're allocated to class A, we have 16 bits for our subnetting, so we have what is that? That is 65,000 subnets. Yes. So we have a lot of subnets there. A lot of places are allocated a /16. A lot of universities have 172.0.0. Or like 172.20.0.0/16. That is what a university might be allocated. So the 172 is 101.0.11.0.0 dot let's see 0.0.0 16.8.4.2.0. Yes, .0.0. 1, 2, 3, 4, 5, 6, 7, 8. 1, 2, 3, 4, 5, 6, 7, 8. So here's the bitwise representation of this /16 allocation, which means that if we use /24 subnetting, then we have 8 bits for the subnet and 8 bits for the host on the subnet, which means we have 256 subnets and 256 IP addresses per subnet, of which we can use 254. Universities love this allocation. You got 256 subnets, you got a couple hundred hosts per subnet. That's perfect. That's a pretty substantial allocation. Okay, let's talk about a couple other things that we can't use. Network 0. If here is a class A starting with 0. I've never actually seen it used, and I don't think it's allocated to anybody, and I think there's a reason for that. I don't really know. I need to do some research, but a network that starts with 0, I just haven't seen it out there, and maybe I'll do some research and figure out why. So avoid that. And it isn't allocated to you anyway, so you really shouldn't be using it anyway. Another thing is the subnet 0. So here is a /24 in a class B network. It's a class B because the first 2 bits are 1, 0. And so the network portion for the class B is the first 16 bits. So here's the subnet portion. These 8 bits is the subnet portion between the natural boundary of our classful network and our host portion, and it's all zeros. Old routers running old versions of iOS can't handle this. New routers can, and there's a command called IP subnet-0 to allow the new routers to handle it, and that command is actually turned on by default in recent versions of iOS. So that's cool. This problem fixes itself. You can use the subnet 0, but if you're using an old router, like you scrounged a 2511 out of a closet somewhere, it's possible you might be running an ancient version of iOS which either can't handle the IP subnet 0, or you need to type in the command IP subnet 0 in order for this to work. Just something else to watch out for. Let's talk about one other type of IP address. It is a special class A subnet. It is the class A subnet starting with 127. This is the last class A before we get to the Class B IP addresses, which start at 128, it's allocated for loopback. So the IP address 127.0.0.1 is traditionally a loopback IP address on Unix boxes. And that way, if the Unix box wants to talk to itself via TCP, it just opens a TCP socket to 127.0.0.1. Now, in actuality, the whole Class A is allocated as loopback. So 127.33.45.2 is still considered a loopback address, although it won't necessarily work as a loopback address on Unix boxes, because typically Unix boxes only have the /32, that specific IP address, considered the loopback address. Okay, so we've got some legal IP addresses that we can use in a /30. Let's go ahead and configure a router with these IP addresses, and we'll see what the router will let us do and what the router won't let us do. So here's a router. We're in what's called user mode because we have this little arrow on the left. We enable, and we type in our password, and then we want to create a loopback interface. A loopback interface is a logical interface on the router. We can create as many as they want because there's no physical hardware associated with it. It's good for management because it's always up. If you're trying to manage your box on a physical interface like an Ethernet interface, and that's how you telnet to the box, and then that Ethernet interface goes down because a cable breaks or something like that, then you can't get to the router to fix it. That's bad. But the nice thing is a loopback interface is always up because there's no hardware to go wrong. So to configure a loopback interface, the first thing you have to do is get into configuration mode. So we'll go into conf terminal. Also, people call that conf t. So now we're in global configuration mode. This is where we can configure things globally throughout the router. But we want to configure a specific interface. So we'll type in interface or int LO for loopback 0. Now loopback 0 doesn't exist yet. We start counting at 0 and go up. You could create interface loopback 3 if you want. Loopback 0 is better to start with loopback 0 because that's what most people do. And so we'll configure our loopback interface. Now we type in IP address 10.35.7.13. Now we wanted our network to be a /30. We'll type in 255.255.255.252. Now what is this? This is the net mask for a /30. Let's go back and take a look at our IP addressing. Here's our IP addressing. Now the net mask for a /30, the net mask is the bits. Here are all the bits for the net mask. These are the bits that are the network. The first 30 bits indicate the network. So you set them all to 1. These 2 bits indicate the host. So you set them to 0. And then if you convert this into decimal, these are all 1, so it's 255. These are all 1, so it's 255. These are all 1, so it's 255. These are not all 1s. If you add these up, it's 252. It's like 255 minus 2 minus 1, so 252. So that way we say that the net mask is 255.255.255.252 for a /30. And that's how we configure the Cisco router. IP address 10.35.7.13, 255.255.255.252. Now, if you remember, the .12 address was not a legal address for that net mask. Let's see what happens when we try to type in IP address 10.35.7.12, 255.255.255.252. Bad mask /30 for address 10.35.7.12. So the router knows that that's a bad address. It can't configure it, so it didn't configure it, and it prints out an error message. Let's try IP address 10.35.7.15, 255, 255, 255, 252. This is the broadcast address for the /30, so this is also an invalid IP address. And again, the router prints out the error message. Cool. It didn't accept the bad command. Okay, let's work on our IP addressing and our net mask for a little bit. We did this with a /30. Now, if we made this a /31, then our net mask would be networked to the 31st bit, which would be a 255.255.255.255.254. So at that point, we have two IP addresses in the subnet. It would be 10.35.7.14 and 10.35.7.15, where the 7.14 is where the host bit is 0, because we only have one host bit, and the 10.35.7.15 is where the host bit would be 1. Now, there's a problem, and the problem is that there's a problem, and the problem is if the host bit is always 0, then let's go back and put the IP address of our host there in bits. Okay, there's the IP address of our host in bits. Here's the network portion, and then the host portion at the end, and the last bit. So here's all the network portion, and then the host portion is a 0 for a .14, or the same thing, copy pastes with a 1 at the end for the .15. Now the problem is you can't have a host that's all zeros. I mean, the host portion can't be all zeros. Here we only have one bit, but in a sense, every bit is 0. You also can't have a host portion that's all ones. Well, so what that means is a /31, even though it has two possible IP addresses inside the /31, neither of those are usable by hosts. So a /31 is pretty useless in the networking world.